Hi everyone. Today we're going to quickly go over the basics of behavioral cloning. Um, behavioral cloning is based on neural networks, and essentially what a neural network is going to do is going to take inputs and outputs and find an algorithm that will get you from those inputs to those outputs. So the goal in a neural network is to find a function that has a high accuracy for the given inputs to the given outputs. For example, if we give a neural network the inputs of, let's say, 1,000 photos of stop signs and 1,000 photos of yield signs, and we try and find a function that will correctly label these as stop signs and yield signs, the neural network will search through several hundred or several thousand functions that will try and produce these accurate stop sign and yield sign labels. So one example as an illustrative purpose is the neural network could say, hey, is there at least 20% red in the photo? And if so, it's probably a stop sign. If not, it's probably a yield sign. And this isn't exactly what neural networks use. They tend to be convolution layers, but just as an example, we're going to go ahead and go with this 20% red idea. So if we train a neural network on these several thousand images with the correct labels, it could produce something that's basically like, is it at least 20% red? And it finds that, hey, when I check my database that I've been given, I get like a 96% accuracy. That's pretty good. So then we say, okay, that's good enough for us, and we'll call that our model. So now we can give our model a new stop sign and a new yield sign, and we can run it through this model to see what output it'll give. So we give it a picture of a stop sign, and we say, is it at least 20% red? And it says yes, so it must be a stop sign. We give it a yield sign. We say, is it at least 20% red? No, so it must be a yield sign. Now, a little bit of a side note on the robustness of neural networks is that if you try and test on something that's outside of your data set, you tend to get poor performance. As again, an illustrative example of how this might happen is if the neural network found something that was basically like, hey, is it at least 20% red? And that works on the data set, but then outside the data set, we're testing on things that are just like black and white photos as well, you could see it fail. So for example, you give it a black and white stop sign, it'll say, is it 20% red? And it says no. So it'll say, oh, it must be a yield sign. And then is the yield sign? No, so yield sign. So, and there's a lot more to this, but for now, just kind of keep in mind that how you build your data set can really affect how it performs in the real world. So behavior cloning is basically taking neural networks and reposing the question in such a way that we can really quickly aggregate data for a particular model. So let's say that we want to train a race car or an RC car how to drive around a track autonomously. So in order to do that with behavioral cloning, what you're going to do is you're going to take the RC car, which let's say has just throttle and steering, and you're going to hook it up with sensors as well. And also a computer that can capture the sensor data and also capture what throttle and steering are put in, but those are excluded in this diagram for now. So what we're going to do is we're going to take the sensors and give them to the human. The human is then going to decide what we want to do in this scenario. So and then we're going to take the human's decision and apply it to the car, of course. So you have the sensor coming into the human then decides a throttle and a steering for the car at that given point. So this can be reframed in the exact same way as we had our previous neural network, where you have some input, some output, and then we're going to try and find a function in the middle that gets those inputs to those outputs. So just like we had earlier, we have a neural network. So after we drive the car around for about 20 laps or so, when we'll have several hundred photos along with corresponding output labels. And we can take those and we can train and get a neural network model, just like we were describing before. And that'll produce a model, which is like a general rule for what to do in a given scenario. So now we can take our photo, let's say this is what the camera captures, and we send it over to our neural network, and the neural network says, hey, based on my general rule, what am I supposed to do in this scenario? And it'll say, well, based on my general rule, I would label this as 100% throttle and steering of 0, where a steering from a positive one would be full right, negative one would be full left. So then we give it another example of an example of a turn, as you can see in the bottom left here. So we give it to our neural network and it says, oh, based on my general rule, this is a 75% throttle and a steering of plus 0.52. And then we can have basically an input and an output that neural network will give us pretty consistently. So now we go back to how we had our system set up earlier, where you have some kind of sensor in this case a camera, going over to the human, and the human decides what to do based on throttle and steering. Now we can replace the human decision with this neural network. Then it gets a new photo and it says, hey, what is my general rule for this photo? And it'll say, I'm pretty sure that the human would have decided to go full throttle here and 0% or maybe plus 0.1 or something to that effect. And it keeps getting these new photos, and then it gets these new labels for the new photos. Then we take those labels and we then run them over to the throttle and steering and actually apply the decision that the neural network had decided on. And then very quickly, you have a neural network that can drive an RC car autonomously by just copying what it sees the human doing. That's called behavioral cloning. That's what we're going to implement in this class. And a quick note on some of the pros and cons of behavioral cloning. One of the really big pros about behavioral cloning is that it works really quickly. It's really easy to get a data set that will perform in a given environment. So in about half an hour, you can collect all the data that you need to get a simple behavioral cloning model to work, and then you just train it. Depending on the speed of your computer, it can be really quick as well. And then you can have an autonomous driving car really quickly. So one of the major downsides to behavioral cloning is that it really can only get as good as the user. So for example, if you have a young child who's learned to drive a car for the first time, they're not going to be very good at driving it. So the model can only copy what the human does, versus if you had a professional RC car driver, theoretically, the behavioral model could get as good as that professional. But that is the major limitation. So for example, if you just did behavior cloning on all of human driving, and let's say we have 1,000 crashes a day, then the behavioral cloning model can only get as good as the 1,000 crashes a day, unless you then remove that data set. So there's a whole bunch more that goes into behavioral cloning, but that's the premise of it.